In this video, we introduce the synthetic multimodal C-SLAM dataset for multi-service robots, the CSE dataset. As service environments have become more diverse and complicated, they have begun to require complex tasks that are difficult for a single robot to handle. This change led to an interest in multiple robots instead of a single robot. As a result, SLAM, the fundamental technology for service robots, has begun to develop to collaborative SLAM, which enables collaboration between multiple service robots. However, despite these progress, C-SLAM remains limited in terms of benchmark datasets compared to SLAM for a single robot. In the case of SLAM datasets for a single robot, there are lots of benchmark datasets, as shown in the figure below. So, what about C-SLAM? Currently, a few C-SLAM datasets for multiple robots are being proposed. For example, in the case of early datasets, there are some datasets, such as Yusha's and Air Museum. However, they are only acquired in static and limited experimental indoor environments. To handle these issues, a few datasets including dynamic objects are proposed. Nevertheless, they are being acquired in outdoor urban scenes or limited indoor environments such as corridors and room-size laboratories. This means that there is a lack of diversity in the environments in terms of the benchmark dataset for C-SLAM. Furthermore, there are no C-SLAM datasets acquired in the service environments for multiple service robots. Therefore, we propose the first synthetic multimodal C-SLAM benchmark datasets for multiple service robots. We provide the realistic C-SLAM datasets covering various challenging cases encountered by real service robots in diverse service environments, such as hospital, office, and warehouse. The main contributions of our dataset CSE are as follows. First, as previously mentioned, we propose the first synthetic multimodal C-SLAM dataset for multi-service robots. Second, we construct datasets in a variety of indoor service environments with various challenging cases. As shown in the video, we include the challenging cases such as homogeneous wall and floor, visual redundancies, and dynamic objects. Third, we configure the more realistic scenarios of service robots by considering inter- and intra-robot loop closures for the appropriate evaluation of C-SLAM algorithms. In addition, we also configure more realistic scenarios by mimicking the movements of real service robots. Finally, based on the simulations, we are able to get the accurate GT poses, precise time-synchronized sensor data, and even guarantee anonymity. This table shows the comparison between the existing C-SLAM datasets and ours. In particular, we divide each environment into static and dynamic, as shown in below figure. This allows for efficient evaluation of SLAM algorithms handling dynamic objects. We also leverage simulation to acquire accurate GT poses and precise time-synchronized sensor data even in the GPS-denied indoor environments. We utilize the NVIDIA Isaac Sim, which provides photorealistic environments and sensor data. Here's introduction of our dataset. As a robot platform, we utilize the NVIDIA Carter, which is a differentiable drive robot with 2 wheels on each side. We also provide the various sensor data such as stereo RGB images, stereo depth images, inertial measurement unit, and GT poses through NVIDIA Isaac Sim. Since these data are based on simulator, they are all exactly time-synchronized, even between different robots. We utilize the ROS navigation stack integrated in Isaac Sim to drive the robot. By leveraging this, we can mimic more realistic service robot movements. In addition, this allows us to build datasets with robot-to-robot and robot-to-human interactions, as shown in the video in the first row. And since each robot uses the same goal points in each static and dynamic environment, they can move on nearly identical trajectories. As shown in the video in the second row. In this page, we describe the considerations we took into account when building scenarios for each robot. To properly evaluate C-SLAM, we build the scenarios that consider intra- and inter-robot loop closures. In particular, for inter-robot loop closures, we categorize scenarios into 3 types: follow, intersection, and revisit. Each type is described on the screen, and the videos below are examples for each type. This video shows the examples of each type occurring in the CSE dataset. This page shows the total scenarios for each robot in dynamic hospital environment. For the hospital environment, we can see that there are lots of revisit areas between robots in most areas. In addition, there is also the case of following the robot from a slightly distant distance, with a total of 2 intersection cases. This page shows the total scenarios for each robot in dynamic office environment. Similar to the dynamic hospital, we can see that there are lots of revisit between robots in most areas. Also, in the office environment, there is no intersection between robots, and it contains one follow case. This page shows the total scenarios for each robot in dynamic warehouse environment. In this environment, all cases are evenly distributed. In particular, in the warehouse environment, there are 2 intersection cases between robots, both of which occur at very close distances. The hospital scene includes 16 humans and has structures like long corridors. Additionally, the hospital scene includes homogeneous walls and floors, as well as visual redundant textures like chairs and doors. The office scene includes 37 humans and has a complex structure with rooms and corridors. Also, the hospital scene includes homogeneous walls, as well as repetitive textures like floors and ceilings among the scene. The warehouse scene includes the most humans, totaling 38, among all scenes. It includes a repetitive structure consists of components like storage racks, which prominently stand out in the scene. The full sequences in the hospital environment is as follows. In this environment, all robots start from different starting points and complete their navigation by returning to their starting points. All of the robot's scenarios consists of driving down long corridors and exploring small spaces. We can see that in both static and dynamic environments, each robot drives through almost identical scenarios. However, for the sequence in the dynamic hospital environment, we can see that the robot's camera view is severely occluded by a number of dynamic objects. This can lead to challenges where the robot makes wrong feature associations. The full sequences in the office environment is as follows. In this environment, all robots start from different starting points. Robot 2 and Robot 3 finish their navigation near their starting points, whereas Robot 1 ends at a different location from its starting point. Robot 2 and Robot 3 drive over a specific region repeatedly, and Robot 1 drives in the overall area of office. As a result, the Robot 1 scenario contains a lot of inter-robot loop closures because it has a lot of overlap with the other robots. In the case of dynamic office, there are lots of humans included. As such, all robots include challenges such as extreme occlusions due to these dynamic objects. The full sequences in the warehouse environment is as follows. All robots start from different starting points and converge in the same space to finish their navigation. In this environment, all robots drive between large, regularly aligned structures. In addition, the all robots scenarios contains many inter-robot loop closures due to the overlap between all the robots. Besides, it also includes challenging cases where intersections are performed at very close distances between robots. This section demonstrates the execution of a SLAM algorithm using our dataset. This is the result of running ORB SLAM 3, one of the single robot SLAM algorithms. In the hospital, the presence of numerous static objects, such as chairs and desks, facilitates easier feature matching, thereby enhancing the accuracy of pose estimation. This is a result of the covens. In the office, the property of office such as complex illumination, repetitive visual pattern can lead covens failure. Unlike decentralized SLAM, centralized SLAM shares a single backend among all robots. So, if even one robot sends an erroneous value to the server, the backend may perform incorrect optimization or stop working, which would affect the performance of all robot. Consequently, we demonstrate the result of swarm SLAM, one of the decentralized C-SLAM. In the warehouse, the redundant structures and repetitive features can degrade the performance of SLAM. Also, the redundant structures can lead to inaccurate loop closure. We evaluated Covin's Swarm Slam, ORB Slam 3, and NVIDIA Fusion on our dataset, and the visualization of the trajectory is shown here. We did not visualize the algorithms that were halted. Please refer to the table in the paper to see if each algorithm was halted or not. We conduct an ablation study using the feature removal module to investigate the impact of dynamic objects on CSLAM. Experiments were carried out in a dynamic environment with Swarm SLAMD that includes feature removal, and without it. We can see that dynamic objects can affect the performance of SLAM, as there is an improvement in performance with Swarm SLAMD over Swarm SLAM. We further analyzed Swarm SLAMD to see if it actually worked. This visualization shows a comparison between Swarm SLAM and Swarm SLAMD in the red boxed areas of the APE graph, showing that Swarm SLAM shows poor performance while Swarm SLAMD shows robust performance. From this experiment, we observed that Swarm SLAM failed to perform proper bundle adjustment between keyframes captured at different times due to the movement of dynamic object. Furthermore, we analyzed the dynamic warehouse sequence where Swarm SLAMD failed. This figure shows the keyframe where Robot 1 and Robot 3 each determined the same place through the place recognition module. As shown in the map, they are different places, and the failure of inter-robot loop closing caused a large performance degradation. This is our summary of the paper. Through all these various characteristics, we expect our CSE dataset will contribute to the advancement of CSLAM research for multiple service robots. Thank you for listening.